keeping in mind that astronauts are often concerned about how their stomachs will behave once they get into weightlessness.
I'll never forget my first flight. We're sitting around the table, and one of my crew members, who it's his first flight, and after the cameras all left, he's got steak and eggs and hash browns and coffee, and he's pouring hot sauce on, and my commander looks over and he says, going for color and distance, I see.
Like the rest of the facilities in crew quarters, the bedrooms are not extravagant, but they work.
It's a very small room. You got a desk, a bed, and a shower and a toilet in the bathroom. Very sparse, but very functional. It's very quiet. It's an elevated floor back here with sound insulation underneath, sound insulation up above, and so weird schedules can actually come in here and get some sleep.
But a quiet room doesn't always do the trick when a launch is waiting the next day.
It's not anxious, it's just you want to get off and do it. And in fact, one of the hardest things, some folks really like coming down to crew quarters and just relaxing a little bit before they fly. And I came down and it was like, I want to launch. We're here, let's launch tomorrow, but you can't do that right away.
A new conference room was built to accommodate the larger crews of the shuttle and International Space Station, including foreign crew members.
This is where they go over all the flight data file, get any changes, updates. They get the weather brief on the screens here. It's a place to come and relax. We have simulators that simulate robotic arm operations for both shuttle and station, as well as a simulator that lets you actually land the space shuttle. And it's a pretty good simulation.
Space is a lousy place to get sick, so specially trained doctors and nurses along with exam rooms are on hand to make sure everyone stays well before heading into orbit.
Pre and post launch, there's examinations that have to be done. You got to see the doc. If anybody got sick while they were in crew quarters, they go see the flight doc and just make sure it's those last minute checks that everything's okay. And it's just they're standard small exam rooms and a private place to meet with the doctor when you're here.
A staff is on hand to take care of all the aspects of an astronaut crew's day, from housekeeping to scheduling.
The people down here are family. They really get to know you. The folks that run crew quarters, they keep it clean, they cook for you. There are friends that I've made for life and have bonded with for my time down here.
As much as the crew quarters is set up to mirror everyday life, there are rooms that are meant solely for the unique demands of going into space.
All right, and of course you guys have seen this on TV hundreds of times. This is the suit room where the crew gets suited up to actually go fly in space. You're tight with the suit techs that are working with you, and it's that last, hey, we're getting ready to go fly in space. This is really, it's a big deal. It's kind of neat.
There's also a launch day tradition that plays out in this room.
Probably the biggest tradition is the game Fargo Possum. And Fargo Possum is low-handed poker. And the rule is you can't leave crew quarters and go to launch until the commander wins the hand, has the lowest hand, and that sometimes takes a while.
All right, we can fly!
Now suited for space and following several days at crew quarters, the astronauts get to take a walk through the corridor to the elevator that will take them to the waiting Astrovan and out to the launch pad. Cabana served as the flight operations director during a number of shuttle missions, watching over the astronauts as they prepared to head into orbit. His advice to flyers was pretty simple. Let it sink in.
Mostly what I tell first-time flyers is when you get ready and you're up in space and you have a free minute, make a memory. Stick your nose up to a window and make a memory, because the eyes God gave you are so much better than any camera. And when you look at a camera picture when you get home, you're disappointed. It's just not as vibrant, it's not as real as it is when you just look out the window and make a memory.
The Space Shuttle could get all the way to space on its own power whenever it launched from NASA's Kennedy Space Center in Florida. But when a shuttle orbiter travels from one place to another here on Earth, it needs a lift, a piggyback ride or ferry flight aboard the shuttle carrier aircraft. It's an unusual sight, a low-flying jumbo jet with a spaceship bolted onto its back.
And it's really amazing to see, first the orbiter in person. It's almost surreal.
The shuttle carrier aircraft is actually a Boeing 747, modified to handle the weight and drag of the shuttle orbiter on its back. It's been supporting the Space Shuttle program ever since the approach and landing tests during the late 1970s. In 1990, NASA added an additional modified 747 to its SCA fleet to make a total of 2 aircraft available for ferry flights. The shuttles began all their space careers with ferry flights when they were first delivered to Kennedy from the manufacturing plant in Palmdale, California. But most of the time, a ferry flight was needed to bring a shuttle back from Edwards Air Force Base in California, following a landing on the West Coast due to poor weather in Florida.
They built the 747. They built a very nice airplane, and it does what you want when you fly it. The only thing that's different is when you're carrying the orbiter, there is a noticeable vibration, and of course the speeds are quite a bit higher. But as far as the feel in the aircraft and the ease with which the aircraft flies, it is deceptively easy.
After an end-of-mission landing at Edwards, it took the landing team about a week, weather permitting, to prepare it for its upcoming cross-country trip. A tail cone was installed to reduce aerodynamic drag and turbulence during the ferry flight. The spacecraft was lifted inside a large gantry-like device called the mate-demate device. The aircraft rolled underneath, and the orbiter was lowered and bolted into place. The team simply reversed the process to remove the shuttle from the plane. Sometimes just getting the shuttle and aircraft ready for the trip could be a test in itself. NASA Flow Director Stephanie Stilson recalls the challenges the ferry flight team encountered in 2005 after Space Shuttle Discovery landed at Edwards at the end of the flight STS.
And everybody thinks the desert, dry, no issues, no rain. Well, we had snow in the mountains, actually struck ice, and we had locusts. So it was like everything that could possibly happen outside of our control happened. But once again, that just gave us a chance to show how we can react to changes and things that we're not expecting.
But the toughest part of a ferry flight is keeping the shuttle safe from harmful weather or other conditions during flight. So, a Pathfinder aircraft flies 100 miles ahead of the attached pair, making sure the flight path is safe and dry.
You don't want to bring it through any turbulence, no visible moisture. There's some temperature limitations. And essentially we're the plane to make sure we don't bring the orbiter through there. So our job is to be very vigilant of any changing weather conditions and to make sure that the orbiter is brought on a safe flight path.
There were 87 ferry flights throughout the Space Shuttle program, including flights for testing, delivery, orbiter upgrades, and of course, end-of-mission landings. Today, the shuttles are being prepared at Kennedy to go on public display at sites across the country. Atlantis won't need an aircraft to move to its new home at the Kennedy Space Center Visitor Complex. But Discovery, Endeavour, and the test orbiter Enterprise will each take one last ride. Discovery will be flown to Dulles International Airport in Virginia and then moved to the nearby Smithsonian Udvar Hazy Center. It will take the place of Enterprise, which will be flown from there to John F. Kennedy International Airport, and then on to the Intrepid Air, Sea, and Space Museum in New York City. Endeavour will be flown to Los Angeles International Airport before making its way to the California Science Center in Los Angeles. The bulky combination of orbiter and aircraft is unmistakable and usually attracts attention from onlookers on the ground as it makes its way across the sky. NASA plans to keep one of the modified 747s for its Stratospheric Observatory for Infrared Astronomy, or SOFIA science program. But as the shuttles make their final ferry flights, space fans along the way may be able to get a glimpse of the duo making one more pass overhead.
It's a great thing to be able to do that, and then if we have any stops along the way, it's a chance for us to share the orbiter with the public in that area that most likely has never even been space shuttle back.
It takes hundreds of dollars to orchestrate a space shuttle launch. Their office on launch is one of the most unique workplaces in the world, a firing room at Kennedy Space Center in Florida. The firing room is the nerve center today.
KC Safety Mission Assurance.
KC Safety Mission Assurance will go, Mike.
Thank you, Mark.
Behind consoles, wearing headsets and checking off countdown 3 miles away. In the firing room, they also send commands to the spacecraft, talk to the astronauts, and communicate with dozens of other teams, from rescuers near the launch pad to mission controllers in Houston. A successful countdown and launch requires the team to complete more than 1,600 steps in order. The checklist is contained in part of the 8-volume set of shuttle launch documentation, covering almost 8,000 pages. The books also contain contingency plans for handling launch scrubs or emergencies.
Range weather.
Weather is green on all constraints. Winds are from 335 degrees, 18.5.
Okay, thank you, Kathy.
Keeping track of the countdown as a whole are the shuttle launch director and the NASA test director, NTDs. In the firing room at consoles on risers. The orbiter test conductors share the second row with the NTDs. In the back of the firing room, facing the 2-story, hold on to come up with solutions to allow a safe liftoff and present them to the launch team. NASA built space for 4 firing rooms on the upper floors of the Launch Control Center at Kennedy during the Apollo program. Each one is dominated by the angled panes of glass that let controllers inside see the spacecraft on the pad and during the first minutes of ascent. The first space shuttle mission launched on April 12, 1981. Controllers in Firing Room 1 had the primary responsibility for the liftoff. The firing room recently renamed Trip and Firing Room for that first crew. Firing Room 2 and 3 also staff. Shuttle launches require 2 active firing rooms, one as the primary and one with senior engineering and management personnel teams. A third firing room is capable of stepping in. Firing Room 4, which had been a conference room during much of the shuttle program, was remodeled and opened in 2005 to give the launch team more room and modern computers. The computers are used to constantly monitor the shuttle's myriad of systems. Simply put, they can pick up minute changes in a system's status before a human could detect it. Late in the launch countdown, the computers run the countdown completely through a set of software called the Ground Launch Sequencer.
We're ready to go.
Thank you very much, Scorch. Appreciate that. NTD, with that, you are clear to launch Atlanta.
Copy. Clear to launch.
The launch control team can intervene to hold a countdown if they see something they don't like, but otherwise, it's the software that retracts the orbiter access arm, the gaseous oxygen vent hood, and commands the Space Shuttle's 3 main engines to ignite.
Roger, roll. Beautiful sight. Yeah. Woo!
Cape Cod, Massachusetts is known for its beautiful beaches. This scenic landscape is also home to one of the most frequent marine mammal stranding sites in the world. Scientists know very little about what causes these animals to strand. What has been proven is that a quick and efficient response in these moments is a matter of life and death.
If we can get there quickly and provide supportive care, they have a much better prognosis in terms of survival.
Katie Moore works on the front lines as the Deputy Vice President of Conservation and Animal Welfare at the International Fund for Animal Welfare. Through Katie's fine-tuned rescue efforts, she has increased the survival rate from 14 to 75%. But the question remains, could it be possible to predict rather than react to these events?
If we can develop an algorithm that pieces together the different variables that may be causing mass strandings or driving mass strandings, then we have the ability to then prevent them. We can have teams that are out on the shore looking for animals in those hot spots, knowing that all those variables have come together and this is the likely point in time where we're likely to see it. But we can also have teams ready to respond so that if they do strand, we're there that much faster and more animals will survive the event.
In Cape Cod, the annual number of stranded animals ranges from less than 10 to over 200. Some of the most affected species include pilot whales and white-sided dolphins, creatures that are typically found in deeper water, rather than along the coast. The ongoing search for answers began 400 miles away at the Bureau of Ocean Energy Management in Sterling, Virginia. There, fellow marine biologist Desiree Reeb had some initial thoughts on triggers for these events.
For the large proportion of these strandings, the animals are across the ages, in pretty good health, and there's no really immediate evidence as to why they actually strand.
Geomagnetic perception, or the ability to navigate using Earth's magnetic field, is a feature thought to exist in marine mammals. Could changes in the magnetic field confuse the animals? All the way down to the sea floor, sensors like magnetometers can detect changes in Earth's magnetic field, called geomagnetic pulses or storms. One cause of such changes is activity from the sun, known as space weather.
Geomagnetic perception is one of the theories, and I thought, well, if a magnetometer can pick it up, maybe the animals actually can pick it up.
Dr. Reeb brought her hypothesis to Antti Pulkkinen, research astrophysicist from the Heliophysics Department at NASA's Goddard Space Flight Center in Greenbelt, Maryland.
The coolest thing was that we realized that nobody had really taken a cold, hard data science analysis look at the problems.
By combining Katie's records on marine mammal strandings in Cape Cod and Antti's records of the changes in Earth's magnetic field, the team of researchers had a starting point.
What we were trying to look at here was if there was a potential driver or relationship or correlation between the occurrence of mass strandings and any solar activity.
The data that we have correlated or analyzed so far is information about the local geomagnetic conditions. We have long data records from geophysical observatories of the local geomagnetic field variations and marine mammal strandings.
When the team analyzed all the data, they found that measurements from the same time period, or random time periods, produced similar results, meaning that there is no obvious relationship between geomagnetic changes and strandings in Cape Cod. If space weather wasn't the trigger, what could be?
The easy fix correlation between a geomagnetic pulse and, a stranding doesn't seem to be very evident, but what it does show is that there are multiple variables involved in this equation, and that the geomagnetic storms could just be one very small part of it. Significant still, but it looks like there are multiple oceanographic and environmental elements.
The scientists considered what other variables may exist in the air or water that could change animal behavior. Tides or winds could be disruptive. Ocean color, measurements of the water's chemical and particle content, could reflect changes in the food chain. Perhaps sea surface temperature was a factor too. With the help of data from NASA Earth Science missions, they could also explore these possibilities.
To me personally, it's really driving also an additional motivation in doing something about this.
With more data on hand, it was time to expand the team. They recruited statisticians and the expertise of NASA Earth Science data analyst and oceanographer Erdem Karakulu.
A data set, no matter its shape or content, always has a story to tell. Trying to figure out how different data are connected, I think, require a wide diversity of skills and background knowledge.
For example, I'll be explaining how a mass stranding occurs and how we respond to try and understand why I'm presenting the data in a certain way. And my colleagues from NASA will look at me and ask questions that I wouldn't think to ask because I take for granted my understanding, and they're coming at it from a totally new angle with no background.
The group hopes to combine these data sets in a way that reveals a pattern, allowing them to predict the likelihood and location of mass strandings before they happen.
We've really just sort of slowly peeled the first layer of this onion back. And I think that there's so many more layers that still need to be addressed and looked at. And I hope that we can actually find additional collaborators, additional funding partners to really bring all the data that's really available to really give this the study and the scrutiny that it deserves.
And we are also going to make all these data sets available to the entire scientific community so that we can utilize the entire scientific community to take an attack and approach this problem.
The project's legacy rests not only in a predictive tool, but also as an example for collaborative research moving forward.
I think that there will be other things to take and run with, get new ideas, maybe add more data. And I'm hoping also that it will be a model for how projects can then be open to the wider public.
We'll just follow you guys that way.
With the potential for an even broader collaboration ahead, Katie's rescue team is optimistic that they will gain a deeper understanding of strandings and ultimately save more lives.
The ability to release animals after they've stranded is tremendous. When we do that, I mean, that's the best feeling in the world after all of that hard work.
Those questions that seem unanswerable, if you give them time and support and effort and put people on them, we can do amazing things.
Welcome to NASA Edge, an inside and outside look at all things NASA. We're joined by Michelle Monk and Steve Gaddis. How you guys doing?
Great.
And we have a very important topic today, and that's going to be EDL, or Entry, Descent, and Landing. Now, Michelle, you're the principal technologist for EDL.
Yes.
What is Entry, Descent, and Landing?
Entry, descent, and landing is how we get a spacecraft from the top of an atmosphere to a planetary surface. So the entry part refers to, the atmospheric flight, most of it, and then we have descent and landing, which is usually propulsive and get us down on the surface safely. We do D and L at places that don't have atmospheres like the moon or, asteroids, but usually we talk about EDL when we talk about atmospheres.
So Michelle, what is your role as principal technologist for EDL?
I look across all the missions that NASA has coming up that will use entry, descent, and landing on any planet, and I look at the technologies we're going to need for those missions, and I bring them forward to the mission directorate for starting funding.
So you have a need in the EDL world, in the community. You're coming up with the technologies that are needed for future missions.
Right.
And so you take some of those technologies that maybe are less mature, hand them off to you.
Right.
And then you mature those technologies.
Design, develop, test, and evaluate.
Is that a pretty easy task, trying to figure out
Not at all.
what technology you're going to need?
Not at all. I have to look at both the human missions that are coming up, so, sending humans to Mars.
Right.
I have to look at the scientific missions that are coming up and all the destinations the scientists want to go to, and I have to kind of rank those and prioritize them and figure out, where they are in terms of maturity and what the best infusion point will be. When is the first mission that can use that technology? And then I have have to figure out what is the best program within STMD for the investment. Is it better to have a university work on it, or a small business, or is it better for a game-changing program element?
And your job is really hard because we're going to be talking about a suite of EDL projects over the next 2 shows because there's so much content in EDL.
There's a lot of
We can't do this into one show.
Absolutely.
So this will be part 1 of 2 parts. So how do you manage all that?
Well, one is it's hard, but it's also fun. And we've got excellent technologists leading every one of these activities, so we all work together, and we all know that we need these technologies, so we're motivated to see them be successful.
We're a very passionate community.
Yes.
I've seen it in all the interviews that we've done. You guys are definitely passionate. Now, the first one that we're going to be talking about is ESM, or Entry Systems Modeling. What is that about?
So that's the first part of it, where they develop these models and simulations to understand how the technology works and how it will be beneficial at a system level. It's very cross-cutting against all the projects, and the plan is to take that data and then infuse it into the projects.
Blair had a chance to go out to NASA Ames Research Center to talk to Mike Barnhart, who is the Integrated EDL Systems Lead. Let's check it out.
Mike, tell me a little bit about Entry Systems Modeling Project. What is it?
So the Entry Systems Modeling Project is tasked with developing a lot of these technologies that are coming from lower technology readiness level, things like academia, and trying to bring them up to a level so that we're ready to help them.
So in this particular situation, we're talking about EDL projects, and so you're actually helping them raise their technology readiness level?
That's right. So any of these things, Orion, Mars 2020, Mars Insight, anybody that's flying anywhere in the solar system and they need to enter an atmosphere, you have to go through an entry, descent, and landing phase. And we don't have all those problems solved. We don't have all those technologies built. And so we're continually trying to improve on our existing technologies and also renew with new ideas. And that's the real purpose of the Entry Systems Modeling Project.
How do we get the data we need to improve the EDL process across these missions?
Right, so that we can do. We have ground facilities, which we rely on a lot. So we have arc jets that we do for material characterization and developing models for material response. We have our shock tubes, which we use to develop radiation models. We have wind tunnels that we use to build aerodynamic models, the dynamic motion of a body as it's flying, that sort of thing. We need to know all that in order to have a successful entry into a planetary atmosphere. So that's the simplest thing that we have access to every day. And then we also have, some amount of flight data. So there was the Orion EFT-1 flight last year, which was very successful, and we can use that to take our models and look at our predictions and then try and back out, exactly how well are we doing, quantify, how well are we predicting that.
You used a lot of data from Are you able to use data from things like MSL and more recent missions to help? Because I know we have limited data on entry.
Yeah, so MSL is a really great example because we flew Medley on MSL, and that allowed us to get some of the only data that we've had on entry at Mars. So heating data, pressure data, which we use to reconstruct the aerodynamics, is a fantastic tool for us, but there's a lot of challenges there as well. So it's really, it takes a village. You need to have your computational models because they're the true flight space that we have here on the ground. We have ground facilities that simulate parts of the flight space, and then ultimately you have a little bit of flight data. And your goal is ground to flight traceability. Let's predict what we do on the ground. Let's predict what we do in the air. And let's see, how far apart are we so that we can quantify when we're designing the next mission exactly where we think we'll be.
Are you sharing that data with all the different EDL potential systems that are being developed?
Absolutely. Absolutely. Everything that we do in the Entry Systems Modeling Project is, for the greater good. We work very closely with academia. So we've got university partners that we are sharing this data with to help improve our models. We share it with other projects. So with radiation modeling, we were working very closely with the InSight project and OSIRIS-REx projects because they had issues with radiation. of heating on their back shell. So they call us because we're the radiation modeling experts, and they say, here's our problem, tell us, how worried do we need to be?
Be worried, be very worried.
Yeah, we're always looking to help everyone else around the agency, and that's really what Space Technology Mission Director is all about, right? Is trying to help
design.
And that's the challenge but with Medley on MSL, that wasn't it?
Absolutely.
The first time we're able to actually see the health of the spacecraft.
As engineers, great that we succeeded, but I want to know if I got an A+ or a C- on the design. So the Medley data allowed us to actually know how we designed the vehicle.
And based on that Medley data, what were the results? They were pretty good, weren't they?
They were fantastic. But we found some things that we didn't know. Radiative heating is important at Mars and at the scale of MSL. We didn't recognize that before.
And now, since it was such an important mission for you guys, now you're going to take it to the next level for Medley 2 for Mars 2020.
For Mars 2020, yeah, we've got that going, and they're right in the middle of their preliminary design phase. They're all excited. They're going to put some new measurements on the back shell.
Yeah, they were actually at Aberdeen Proving Ground last week doing some testing to see where to put the pressure measurement on the back of the vehicle.
Right.
So yeah, it's really exciting to get this new data in the back shell and using new sensors.
We know Blair had a chance to sit down with Mark Schoenenberger, who's the reconstruction lead, which I got to ask you about that when we come back, because I never heard of a reconstruction lead, but we're going to learn more about Medley 2. Let's check it out.
So Mark, when we think about the differences between Medley 1 and Medley 2, it's interesting because Medley 1, the M stood for MSL, Mars Science Laboratory. Now it's Mars 2020. You guys caught a break. You get to use the same letter.
We still get to use the same letter. I think it'll just be shortened to Mars, EDL instrumentation, and it'll hopefully continue for a bunch more Medleys, Medley 3, 4. We can always call it Mars.
Perfect. It's a nice little series you got going.
Yep. And yep. We're getting great data. So.
Now I'm wondering though, in terms of technology and in terms of how you're growing, Medley. I mean, Medley 1 was a very successful mission as far as the data we got back. Mm-hmm. What are we expecting for Medley 2?
For Medley 2, it's really to dig in and look at the pieces that we couldn't quite get for Medley 1. The instrumentation there was it was the first time we'd flown instrumentation since Viking to get pressure and heating data. So we really tried to capture the whole event. And to do that, especially for pressures, we had these transducers that could see the peak high pressure as you went through the hypersonic phase, and you're really slowing down around Mach 18. And then as you slow down, you really start getting in the noise there with the kind of information you can get. The signal was just really weak. It's sort of like using your bathroom scale to measure the ingredients for a cake. It's just, there's not a lot of resolution there. So it's tough. You don't really trust those measurements.
That's about how my cakes turn out, as if I measured ingredients with it.
So what we did here now is to use more of a postal scale for pressure. So we're measuring down at the low range when we're flying supersonically. Right as we get near parachute deploy, we're spending a lot of time just kind of slowing down, flying at the same altitude, but you're really at terminal velocity. You're not slowing down real well.
Now, is that pretty much in the part of the descent, if you will, that where you've burned away most of the heat shield that you're going to in the process?
Yeah, all the heating's over. I mean, it's still a little warm and things are kind of winding down, but yeah, all the exciting heating stuff is over, and you're really just trying to bleed off energy until you get down to a condition that's safe for the parachute. And so any error in your prediction of how that vehicle slows down, or your prediction of what the atmosphere is going to end up being on the day at Mars, can lead to being far uprange or far downrange. Your landing ellipse and how you target it, you need to account for that. So if we can get better data to characterize the aerodynamics, we can tighten that up and land in even smaller spaces.
Which is always the goal, right?
Yep.
You're trying to find out exactly where you need to land.
Yep.
So Mark, how is the instrumentation different on Medley 2 from Medley 1?
So, at least from my experiences with the pressure side, Medley 1 was really designed to capture the pressure all the way through entry. So it had this nice high maximum pressure it could measure. What we really wanted to do for Medley 2 was to look for the low pressures right before chute deploy. We're going to be coasting there, slowing down from, say, Mach 4 down to Mach 2 for a minute, 100 seconds, something like that. And that adds to the landing ellipse, any error in aerodynamics. So the transducers, we put more of them on the heat shield, and they're at a lower range, so they'll have much better resolution at those low speeds. So we can pull out things like winds, and we can get a better estimate of the drag. And we also have a pressure transducer on the backside. As you slow down, get down to supersonic speeds, the pressures on the back shell become a big contributor to the total forces acting on the capsule. And it's really hard to predict, actually, what those pressures are. So with some truth on the backside, that can really help us nail down the total behavior of the capsule as it's flying at those low speeds.
It seems like we're getting an awful lot of good data on the things that are happening during EDL and Mars, especially for Medley and Medley 2. Are we able to, in the future, maybe translate what you're doing here to potential different atmospheres or different EDL circumstances?
Absolutely. So Medley 1 definitely demonstrated, and it was the reason I think we have Medley 2, was it became the model of how you put an instrument package on a heat shield, how to work with the project to do it, so that they're not scared about putting holes in their pristine heat shield that's designed to keep their rover on the ground. We have a process now to do that. So you'll see missions going to Venus or Jupiter, Titan, those kinds of things. They'll all have instrumentation during entry, and NASA has the confidence to require that because we did so well with Medley 1, and hopefully again with Medley 2.
Mark did a really nice job discussing Medley 2, but I have to ask the question, in all my years at NASA, talking to subject matter experts from all 10 centers, what is a reconstruction lead?
Reconstruction is really important after a flight to understand exactly how and where the vehicle flew.
Oh, okay.
And without the proper data, it's really hard. You have to make some assumptions.
Okay.
So for instance, before Medley, when we didn't have an independent pressure measurement, we had to assume something about the aerodynamics of the vehicle in order to figure out how it flew.
Okay.
Now with that independent pressure measurement, we can nail it and we don't have to make any assumptions. So reconstruction lead is really key to understanding how we did.
See, you learn something new every day. I had no clue.
Yeah, he comes back up with that flight plan that they had and where the data is along those flight plans. It's very important.
Now, speaking of that flight plan, with Medley 2, can you take the data from Medley 1 and kind of show what the flight plan is going to be for Mars 2020, or is that a completely different flight plan?
It's a lot the same because it's the same shape, size, vehicle. The mass will probably be a little different. They're using the same entry, descent, and landing system, but the atmosphere obviously will be a little bit different. The entry velocity will be a little bit different because of the different year.
Right.
But largely, we're going to use all of our MSL simulations as the basis for where we start on 2020.
No, I know, Steve, with game changing, you take technologies and you take them from a technology readiness level. We always talked about that 1 through that 9 scale.
Yeah.
And you're in that middle range.
Middle range, about 3 to 5 or 6.
Right. So, but with Medley, since you have proven you have a flight underneath you, and then you're working on Medley 2, is that still considered, technology at that level?
Yeah,
it's still not space ready.
Yeah, and it was like what Michelle was telling you was we learned so much through Medley 1 that we want to put different kinds of transducers to get the lower pressure range. We want to understand the back shell pressures and radiation rates. So we learned so much, so it's not really just a repeat of Medley 1.
Yeah, we have totally new sensors. Knowing what we know from Medley 1, we've moved a lot of our sensors, so we have kind of the same number of channels of data, but we've distributed them differently on the forebody and then moved some to the back of the vehicle.
Well, speaking of a new mission, we also have now, instead of Medley 2, we also have HIAD 2.
Yep.
Absolutely.
Which is a hypersonic aerodynamic inflatable decelerator.
Inflatable aerodynamic, yes.
Oh, we did it again. It's a hypersonic inflatable aerodynamic decelerator?
Yes.
Very cool.
Bravo.
All right, so that's a completely different type of EDL system from Medley 2.
It is.
And Franklin had a chance to sit down with the project manager, Joe Del Corso.
Yes.
And we're going to learn more about HIAD 2, so let's check that out.
So Joe, we're talking about HIAD 2. Tell me what has changed since HIAD 1. So we've had a number of changes. The first one was we upgraded our thermal protection system. In HIAD 1, we used a Generation 1 thermal protection system, which was somewhat capable. It's low temperature capable, basically something on the order of 1,000 to 1,100 degrees Celsius on the surface. For HIAD 2, what we've looked at is much higher temperature capable materials, much more flexible and lighter weight. So now we're using custom built silicon carbide materials as an outer fabric. We're using COTS materials and some custom materials for our insulator systems. And then on the backside for the gas barrier, you have woven fabrics with PTFE film wrapped around it. Our inflatable structure is also being upgraded. And then the other thing that we're doing is we are working on scalability. We're focusing on trying to get to a 12-meter scale. In order to do that, we've got to upgrade a lot of our equipment. We've got to work on something as simple as just picking up one of the gore seams. It takes a lot of development, a lot of careful coordination. So what we're focused on is not just upgrading our materials, but also upgrading our handling techniques, our manufacturing techniques.
Tell me about the HIAD timeline from the time it was conceived to where we are right now with HIAD 2.
So HIAD has been in development, previously it wasn't known as HIAD, but it's been in development now for almost a decade, and we still have probably another 4 years worth of work to do to get us to human access to Mars. We started out in 2006 doing material testing, and really all we were doing is we were doing low-level, trying to learn how to test fabric systems so that we could simulate an atmospheric entry condition. We were learning how to learn in the early phases. We had IRVI-1 happen. Unfortunately, there was a launch vehicle anomaly, so we lost that. But what it did do is enabled us to put in place IRVI-2 flight tests. People had enough confidence in what we were doing that they allowed us to build a build-to-print. That went up on a sounding rocket launched out of Wallops, and it was an incredibly successful proof of concept. We had an inflatable structure, but no real TPS at the time, thermal protection system. Following the success of IRVI-2, we started out what we currently know as HIAD, which is the Hypersonic Inflatable Aerodynamic Decelerator project. During that project, we were doing all the lab scale development, small scale, little samples. We had learned how to do the initial testing. Now we were taking it through a maturation process, getting it ready for flight again. The third flight that we flew out of Wallops again was called IRVI-3. That was a much higher heating condition, and it was the first chance for us to actually test a thermal protection system with our inflatable structure. After the success of IRVI-3 and the closure of the initial HIAD, we attempted to fly an orbital entry flight test called THOR, the Terrestrial HIAD Orbital Reentry Flight Test. Unfortunately, due to the ORB-3 failure, we had to cancel THOR and we went back to a ground development effort. But unlike the first two ground development efforts, the third one wasn't focused on learning how to test or testing materials or developing materials. It's focused on scaling. So we did small scale in the early development phases, and now we're scaling to something more applicable for human access to Mars.
Now the cool thing I understand about HIAD 2, that you guys have a partnership with ULA?
Yeah.
Let's talk about that.
So about a year ago, ULA announced that they wanted to use HIAD technology to recover their boosters as part of their new business model, affordability. And so we've been working on a flight demonstration with them over the last year and a half.
Yeah, and that would be at the 6-meter scale, which is about halfway to what ULA would need for their full booster recovery, 12 meters that Joe talked about on the video. And it's also the right scale for us to do maybe a technology demonstration mission leading up to putting humans on Mars.
So the idea is that you're using this HIAD technology to recover the first stage of a ULA rocket. And so is that going to be recoverable, and is that going to sort of land in the ocean? Is it going to land on dry land? How is that going to work?
They actually want to snatch it out of midair with a helicopter and to minimize any refurbishment costs.
Wait a minute, so you're going to have this booster coming down with the HIAD
talking about when we're talking about ancient biosignatures.
This part of Western Australia, called the Pilbara specifically, it's really absolutely a mecca for understanding the record of life on Earth. This is one of the most important places on the planet, geologically speaking.
Members of the science team came out here to look at some of the oldest rocks that are on Earth. These rocks are anywhere from 2.5 to 3.5 billion years old, about the same age as the rocks that we're going to find on Mars. And what's very special about them is they have evidence of the earliest life on Earth.
The rocks you see right in front of me here, these wrinkly layered structures that we call stromatolites. Structures like this actually represent fossilized microbial mats.
A microbial mat is actually a structure preserved in the rock made by communities of millions and millions of microorganisms.
Basically fossilized pond scum in a sense. Microbes, bacteria living in a shallow water environment. And we believe that if life ever existed on Mars, it would have been purely microbial.
And those are left behind in the record that are very distinctive. And so we've been showing the NASA and European Space Agency scientists the details of what those textures look like.
When we say with Mars 2020 we're seeking the signs of ancient life on Mars, this is precisely the kinds of signs of life that we'll be seeking.
I've learned to be a kind of a Martian, to be in a harsh environment. My comfort zone is the laboratory, but you know, here I can see that this is the real stuff. It's not just simulating stuff in the laboratory. This is a real good training for us.
It was really important to get the science team out here, and speaking for myself, I had seen pictures of rocks like this, and they didn't really convince me that they were the product of life. And when you see them up close and personal, it really tells the story that this was once life. And that's something you just can't get if you don't go out and look at rocks like this.
You can study it, you can read about it, but there's nothing like the practical experience of trekking around in the desert and really trying to think about, as we land our Mars rovers there and we look at the images provided by our sensors, how do we interpret that and follow the clues to try to find the kind of evidence that has been unearthed here in Australia.
Could Mars ever have supported life? And then to take the next step, did Mars ever host life?
We're just smart enough now about Mars to ask the really hard questions.
These are sounds of our times. Called telemetry, it is the way satellites orbiting in space report to controllers on Earth. Each spacecraft has its own signature, a unique tone. Engineers call it data. You may see it later as a weather report or a television picture from around the world. Space down to Earth with application satellites. What they are, what they're doing for you now, and what will be happening in the decade of the 70s. Weather, communications, Earth resources. These will be among the main topics for dialogue in the 1970s. Each has its own type of impact on our lifestyles. At times, we will be more concerned about one than the other, but always they will be there. Case in point, weather. Spacecraft, like Tyros, Nimbus, and the application technology satellites. Satellites that return daily weather information over the entire world. What do they report? A continuous watch of the Earth's moving cloud cover, tracking storms, measuring winds. recording temperatures at different heights, and testing the moisture content of the atmosphere. As a result, computer systems are built that can receive and analyze vast amounts of global information from many sources, making forecasting more accurate. Hurricanes with their devastating winds and flood-causing rains, a perennial threat. In 1969, Hurricane Camille was first observed and then tracked by satellite. Because the storm's arrival was predicted accurately enough in advance, it was possible to evacuate people from the Gulf Coast. Without this early warning, the Weather Bureau estimated that 50,000 people might have been killed. In contrast, during Hurricane Laurie in November 1969, observations and tracking by satellite enabled the weather forecasters to predict that Laurie would not strike the coast. It is estimated that $3 million was saved from this satellite-prompted decision not to evacuate and not to protect property. TIROS, Television Infrared Operational Satellite. Over the past 10 years, 20 of these hatbox-shaped satellites have been successfully launched for use by NASA and the Weather Bureau. The television eyes of TIROS scan the entire globe daily, reporting on cloud cover and warning of major storms. Since the first operational weather satellites started clicking off pictures, roughly 600 severe storms have been detected, followed, and predictions made about their course. They have sent back more than 1 million pictures of weather conditions around the globe. Cameras on board the Applications Technology satellite scan the Earth and return color images as often as every 20 minutes. Here's a view showing 6 hurricanes on one picture. This near continuous surveillance of 40% of the Earth's surface has proven so useful that the reports have been incorporated into routine weather forecasts and have pointed the way for even more sophisticated meteorological satellites. Major airlines make use of satellite data in planning their flights. Pilots routinely receive weather photos of their transoceanic routes. Before satellite tracking of hurricanes, U.S. Navy hurricane hunters had to search out the killer storms. Weather satellites now locate the storms, and the Navy flies directly to them to make their measurements. The Navy also uses weather satellite pictures for ice patrols. Remote stations in the Antarctic benefit too. Giant resupply ski planes can be safely scheduled for landings in the icy outposts without worrying about being trapped by snowstorms. Supply ships benefit from improved scheduling as well. A recent satellite in the TIROS series does the work of 2 spacecraft. Carrying twice as many cameras, it's capable of discerning cloud formations as small as 2 miles across. The improved TIROS operational satellite carries a proton monitoring instrument that helps spot solar flares. The same instrument can measure the amount of heat reflected from and absorbed by the Earth's atmosphere. This is very important in weather forecasting. In addition, radio frequencies affected by solar storms can be changed in advance, and manned flights to the moon better planned. Nimbus, research and development craft studying advanced techniques and concepts for meteorological Earth observations. Nimbus is measuring the atmosphere's temperature and moisture at various altitudes, as well as making day and nighttime cloud photographs. These measurements are considered the key to accurate long-range weather forecasts. By the end of this decade, forecasts made 1 week in advance will be as accurate as those now made 24 or 48 hours ahead. Satellites and weather are global in nature. Every nation in the world can benefit from the automatic picture transmissions of U.S. weather satellites. Over 50 countries are now using inexpensive automatic picture readout equipment to view daily weather patterns over their own territory. These same countries also benefit from cloud picture mosaics, routinely made available by the Weather Bureau to Europe, Asia, Australia, and North and South America. The weather mosaic is built up from individual weather photos and processed by computer. It is then retransmitted by a satellite. There are three main objectives for an effective meteorological program. The first, global cloud cover photography, enabling us to identify and track storms and to observe their formation and dissipation. This is valuable in the analysis of current weather and the prediction of 24 to 36-hour changes. The second objective, continuous viewing of the atmosphere, needed to keep significant portions of the Earth's cloud cover under constant surveillance and providing essential early warning on rapidly developing weather phenomena, such as thunderstorms and the formation, growth, and death of tornadoes. This information is valuable for short period forecasts of less than 12 hours. The third objective, a global atmospheric research program. Its goal, long-range weather prediction on a worldwide basis. In 1976, scientists from governments, industries, and universities in many countries will meet to work out the problems of international weather forecasting. The Global Research Program will use computers to design and test theoretical models of atmospheric behavior. When the mathematical models are combined with information returned from already operating satellites, it may be possible to make forecasts 2 to 3 weeks in advance. Communications. Some of the greatest strides in putting space to work have taken place in this field. In 1960, Americans made 100 billion telephone calls. In 1969, nearly 200 billion were made. New uses are continually being found for telecommunications. Banks, stock exchanges, hotel reservations, cable TV, hospitals, computer centers, and other new customers are appearing at an increasing rate. We are in the midst of a global communications explosion. Helping meet this demand are communications satellites.
This is President Eisenhower speaking. It is a great personal satisfaction to participate in this first experiment in communications involving the use of the satellite balloon known as ECHO. This is
August 12, 1960. President Eisenhower took part in the historic first transmission via ECHO satellite. By bouncing radio waves off its shiny surface, it made possible long-distance telephone conversations and the transmission of photographs and music. Other communication satellites followed. Telstar, Relay, SYNCOM, each a research step leading to commercial spacecraft capable of handling satellite communications. In 1964, television viewers around the world were able to watch the Olympics from Tokyo. A visit to Mexico City by the Pope was also viewed globally. Over 500 million people, 1/6 of the world's population, saw man's first steps on the moon. Color coverage of space recovery operations from mid-ocean is now routine. At the Manned Spacecraft Center in Houston, doctors discussed space medicine and early cancer detection. The proceedings were telecast live via communication satellite and provided two-way voice circuits between the United States and 3 European countries. The closed-circuit telecast enabled 30,000 European doctors to hear the 3-hour transatlantic conference. One of the best ways to check out new concepts and techniques in communications, navigation, and meteorology is with research and development spacecraft. The applications technology satellites are just that, serving as platforms for testing out new concepts in all these disciplines. The ATS program consists of 7 flight missions. 5 of these have already been flown. Probably the most unique characteristic of the ATS is their ability to receive and transmit from a number of widely separated ground stations simultaneously. They can handle telephone calls, transmit television, teletype, radio voice, and weather data all at the same time. Keeping in contact with the SS Santa Lucia as it steamed between New Jersey and Chile, ATS demonstrated the feasibility of using satellites for high-quality, reliable, ship-to-shore communications over long distances. A similar test was made with a U.S. Coast Guard ship. ATS has been used to relay information from remote instruments and buoys, a step toward future data relay satellite systems. A successful experiment to transmit television by satellite from the east to the west coast took place with the help of the Corporation for Public Broadcasting.
These current tests are enabling NASA and the broadcasting community to iron out technical problems that are involved in this form of transmission and to determine the costs of such future operations. If these tests are successful, and we have every reason to believe that they will be, the American people will reap a major domestic dividend from the national space effort.
The program was relayed from a ground station in Rosman, North Carolina, through the ATS to KCET-TV, the educational station in Los Angeles. As soon as the receiving equipment is operating, Alaskans will have educational radio and television programs beamed to their state. Through an agreement signed with India, an applications technology satellite, similar to the one shown in this artist's concept, will begin telecasting instructional television into 5,000 Indian villages by 1974. India will provide the TV programs. The results of this cooperative experiment are expected to provide an understanding of the effectiveness of satellite systems in meeting the needs of other developing countries. A satellite-to-satellite laser communication experiment is also planned on future ATS spacecraft. Beams emitted by a laser can carry immense quantities of information. Communication satellites hold great promise for navigation and traffic control. Today, airplanes flying over wide open areas of the ocean out of radio range for periods of an hour or more. The problem is compounded by the